So we're now in a position to carry on with networks that are capable of learning from data, where the data set is constructed so that there are output patterns which are desired associated with specific input patterns. This introduces us to the much broader field of machine learning, and some of the immediate considerations would apply to machine learning methods which are different from the backpropagation algorithm, maybe even which differ from the whole field of neural networks. When we are fitting a model to some data, there are some general questions that arise, and we're just going to take a very brief glance at some of these. We need to address two topics. One is bias, and the other is generalization. Bias refers, as it were, to the tendency of the model to impose its own view on the data. Generalization speaks rather of the capacity of a trained system, of a fitted model, to generalize, that is, to apply to unseen data points. So they're the two things we're going to look at. First of all, consider these simple data. The illustrated circles all lie more or less on a parabola. And in fact, we can think of them as having been generated by picking points on the parabola and adding a little bit of noise to move them up or down or sideways or something like this. So that the circles represent an empirical view of an underlying function, the actual generating function. H of x is shown here. Now, if we were to fit a model to these, that model must be appropriate for the data. And it's not always clear what is appropriate for the data. Here, I've suggested to you that the data have their origin in a parabolic function, and so fitting a parabola would definitely be a good idea. But we only know that because we made the data. If we fit a straight line like g of x there, it's going to be a lousy, lousy fit. One could say that the model is not flexible enough. It's only going to do very specific things, and it's not going to change on the basis of your data. That's more or less what we mean when we say it's biased. It has a high bias. It's not sufficiently influenced by the data. Now, a straight line is a very simple model with two parameters. Looks like these data could do with a slightly more powerful model. So on the right-hand side, the blue line shows a fit of a more powerful model. And here you can see that what it's done is the model has accurately hit every single point in the training set, but it's kind of missed the obvious, the underlying generative function. It has fitted exactly what we told it to do, which means that the data points and nothing but the data points are generated by the model. Ideally, in an ideal world, our model would discover the underlying function, any underlying systematicity or regularity to our data. In practice, we can never know that. That may be entirely undiscoverable. So we always have to worry whether a fitted model, a model that has reduced its error as far as possible, whether it is sufficiently attentive to the data by not exhibiting a strong high bias, but also not overly influenced by the data. Here's another illustration of this. Here are four plots, four models. We call them the 0th level, the 1st level, the 3rd level, and the 9th level model. M equals 0 is fitting simply a 0-level polynomial. That is to say, it's just fitting a constant term to the data. So that's going to be a horizontal straight line, and it's going to fit the best horizontal straight line it can, and that's just not going to be very good, is it? If we allow two parameters, we end up with a first-order linear model in the top right hand. You can see it's a bit better than the horizontal line, but it's still not good. In fact, of course, the green line tells us what the right answer is. These data were generated from a cubic function with a little bit of noise. And when the order of the model goes up to 3, we're fitting a cubic function. And you can see it's a really good fit to the data. And furthermore, if we get new data points that are generated in the same way, we have every reason to believe that this model will make accurate predictions about them. The cubic fit is also a very simple curve. You may have seen rather ridiculous use of it by American politicians of late. No matter, we'll move on. On the right-hand side, at the bottom right, you can see a ninth order polynomial fit to these same data. That means that the curve that's fitted not only has a linear term and a squared term and a cubic term, it has terms of x to the 4, 5, 6, 7, 8, and 9. Adding additional terms like this to a curve makes it more pliable. It can fit data better. And when we fit it to these data points, the red line is the fitted model, and it hits the training points perfectly, but it has completely messed up any resemblance to the underlying generative function. This no longer looks like a cubic, and we would have no confidence that this model will produce a good answer if it is exposed to data on which it was not trained. Now, once more, we are illustrating the problem here in a highly unusual situation in which we know the right answer. The right answer is the green curve. It's a cubic. And here we can see clearly that the third order model is correct. But in general, we do not know the underlying function. So we have to bear this in mind. And when we're going then to design a network to solve a task, we've got lots of choices ahead of us. One thing we have to ask is how many layers, how many units in each layer. And the tendency is, of course, to throw the kitchen sink at it, use as much as you have computing power. But consider this case. You've got a large network with 10,000 hidden units, so you've got computational power up the wazoo, or a small network with 3 hidden units. Now, just in general, I don't know, I'm not applying this to any specific problem, but the bias problem is more likely to arise, I think you'll see, for the small network with 3 hidden units. It only has a few parameters, and it'll do the best fit it can to the data using those few parameters. But if the data are interestingly various, it will have a hard time. The large network with 10,000 hidden units has a different danger. The danger here is that we will fit too well to the training data, but in a manner that doesn't generalize to novel data. That is, it will capture not only the underlying structure of the data that generated it, but also the randomness or the noise that is in the data set. I can illustrate that once more. Here we see 4 cases. The left-hand column has degree 1 models, that is fitting a straight line. And the right-hand column is fitting a 10th order polynomial, so much higher order, many more parameters, a much more powerful model. The underlying generation function is the red line, which is the same in all these plots. Up at the top left, we have only 20 data points in our training set. And you can see that the straight line does not too bad. It's not too far off the red line. But it's never going to be a first order model is not going to be a good fit. But it gives more or less the same answer in the bottom left plot when n equals 200. That is when our training set is much larger. Now compare the 2 10th order models on the right hand side. In the top right hand plot we have again a small training set with 20 patterns, and we have a very powerful model. And it has fit this wonky curve that is going to be absolutely useless. But the 10th order model comes into its own when our training set is big enough. So in the bottom right hand corner you can see we've got 200 elements in our training set, and you can see that the fit of the model to the data is extremely good. So there's always this trade-off between having an inflexible model which exhibits bias, or having an overpowered model which captures the noise and misses generalities. We can assume, in general, that every training set will, if it's anyway complex, will speak of an underlying reality that has some kind of structure, but that it will not represent that entirely faithfully, that there will always be some noise in the training set. We can further expect that when we have trained our network or trained our model, and we now bring in new data, these new data will also have some noise, but it won't be the same noise as in the training set. So if we just train on the training set, there will come a time when our model is no longer being influenced by the underlying structure that generated the data. There will come a time when any further fine adjustments we do are responding somewhat stochastically, that is at random, to the noise in the set. For this reason, if we have a sufficiently large data set that we would like to train our model on, it's entirely conventional to split that training set into two sets, one to be used in training, and a separate one which is not used to fit the model, but is used to evaluate the model after fitting. The way this works then is that we will begin training and we will see a decrease in the error associated with the model as we go on training, and that error will continue to decrease through the magic of gradient descent and will never go up again. There comes a point in time, however, at which it is no longer being influenced by the underlying generative structure of the data. And we can see this by occasionally taking our test set and checking it against the model, that is, presenting novel input patterns that the model has never seen before, because they're in the test set, not the training set. Looking at their output, don't change the weights. We're not changing the weights here, we're just evaluating the model. And its performance on this test set will also improve at the start as the model is learning the underlying generative structure. But there will come a point in time at which performance on the test set will begin to get worse, while performance on the training set is still going down, the error is still decreasing. So looking at this, you could say, well, this is handy. Now we can see that, well, the right place to stop training would be when its performance on the test set starts to go up. And that's right, that the best model that we will get here is one which is trained on the training set, but where we choose to stop training based on its performance on an independent test set. And here's a little conundrum. This bites the data scientists every time. The finished model now needs to be evaluated. The finished model is a function not only of our model fitting, but also of our use of the test set. That is, the test set which was not used to set the weights, was nevertheless used to decide when to stop training. So an actual evaluation of the final model requires a further test set. So, assuming we have a domain which is large enough that we can have basically unlimited patterns, the conventional process is to train the model using a training set, but reserve some as an independent validation set that's used only to determine when to stop, and we stop training when performance on this independent validation set gets worse, and then evaluate the model using a further independent set. Those kind of considerations on bias and generalization and the structure of the training set, they apply in most machine learning situations and are not in any sense specific to feed-forward networks trained by backpropagation. It's useful to know the immediate questions that will arise in this domain.